It's my pleasure to introduce Dr. Catherine from Pacific Northwest National Labs. Thank you, Dr. Catherine.
Hi, guys. So can you see me and hear me?
Yes, I don't think we can see your screen yet.
Oh, no, but I tried to share my video just to give you all a wave, say
Oh,
hello,
okay.
and then I'll turn it off because I'm aware that bandwidth is a problem.
Perfect.
So hello, I am a real person. And now I'll disappear. So I wanted to start out actually saying thank you guys so much for joining us this morning. For those of you who do continue on into research careers, I think you'll find that your favorite thing to do is talk about the work that you do, at least once you get over your own imposter syndrome. So you guys are really giving us a wonderful opportunity to share what we do, and on a Saturday morning. So thank you, thank you. All right. So today I'll be talking about innovations in carbon management at PNNL. I sort of like the prior speakers. I'm going to go ahead and give a broad overview of the work that's done at PNNL and then drill into some more specific work that I do. I am a computational hydrogeologist, so that means that all the work I do is on the computer. I'm trying to simulate these processes that we're observing in the field or in our labs. And then I'm also building decision tools, and we'll talk about that. Before I jump into my slides, I'm going to try to show a video. I haven't done this yet in Teams, so thank y'all for being my guinea pigs. I think I can get this to work. But I really like this video. It's got some nice inspirational music, so I'm going to try to give it a shot and see if it'll work for you.
Addressing the nation's long-term energy needs will require fundamental shifts in the way we acquire and use energy resources. Researchers at the Pacific Northwest National Laboratory are working to develop and commercialize technologies critical to decarbonizing the power and industrial sectors. While renewable power generation is expected to double by 2050, natural gas use will continue to grow. Collaborating with our partners in industry and at the U.S. Department of Energy, PNNL is working to drive down the cost of carbon capture from gas power plants. We do this by integrating chemistry, material science, and process engineering to develop novel approaches to remove carbon dioxide from the atmosphere and from power plant and industrial flue gas streams and convert it into valuable chemicals. We're also advancing technologies to safely and permanently store excess captured carbon dioxide in subsurface reservoirs. One study in Wallula, Washington, showed for the first time that basalt rocks can convert a large fraction of carbon dioxide into solid minerals in less than a decade. PNNL switchable solid oxide fuel cells could provide operators with flexible systems for generating hydrogen, power, and grid services. Our solid phase processing approach is transforming the way we manufacture metals. These award-winning advancements could improve the cost and performance of components critical to the fossil energy sector. By pairing scientific discoveries together with engineering, PNNL's technologies are making real-world impacts. Learn more at availablетechnologies.pnnl.gov.
All right, so hopefully that worked. I know it's kind of cheating to show a video during one of your presentations, but I like showing that video in particular because it does give you a glimpse of our actual our facilities, of our labs. Those are the inside of our labs, and the people that you saw in our video are my colleagues. Plus you get some inspirational music. All right. So at PNNL, here, hang on sorry, I just want to go into the correct presentation mode here for me. Okay. All right. So at PNNL, we do work that spans all of the CCUS acronym, so carbon capture, utilization, storage, and more. And so my specialty is in the storage or decision tools components. I will briefly mention that, you know, in the capture space, we are focusing our research for DOE's Basic Energy Sciences Separations Program. That work is focused on understanding the fundamental processes that govern CO2 behaviors at a more molecular level. So this work enables us to partner with industry under DOE FE's carbon capture program to improve existing capture technologies. And we recently developed a capture solvent that breaks the long-standing $50 per ton CO2 cost barrier. This is a big deal in this field. And this critical target brings the $50 per ton 45Q tax credit within reach for fossil power plants pursuing near zero emissions targets. So our pre and post combustion solvents offer opportunities to capture CO2 from bioenergy facilities, which coupled with geologic storage could provide net negative emissions under you know, our existing and future policy incentives. So research is currently underway to integrate our sorbent technology developed originally to scrub CO2 from breathing air on submarines. That's true of all, I think, CO2 capture technology. That's where it began, with submarines. So we're trying to integrate that sorbent technology into more cost-effective solutions for direct air capture. In terms of utilization, we bring expertise in separations, catalysis, systems integration, and engineering to develop utilization pathways. Under that Basic Energy Sciences mission, we discovered that CO2 is much more reactive in solvent than when it is removed at the end of the full capture process. So that's really fantastic, actually. So combining that fundamental discovery with our expertise in catalysis, we've been able to convert CO2 in that more reactive state directly to methanol. And so the PNNL team is currently collaborating with our colleagues at Southern California Gas to commercialize and deploy that integrated CO2 capture and conversion to methanol technology. We call it IC3M. And so like slingshotting around the moon to reduce fuel use on space missions, that IC3M approach is using the thermodynamics to our advantage. Reacting the CO2 while it's in that captured state eliminates the energy required to regenerate the CO2 solvent, while also reducing the amount of energy required to upgrade the CO2 into a high-value commodity. Now, neither of those are really my research areas. I'm going to include links in the chat if you want to know more, if that's your area of research. I'm including some videos in our chat, and then also if you go out to our carbon management website, you can find some more information about that work that we do in capture and utilization. So as I mentioned, my expertise is in storage and building these decision tools. That's what I'll spend most of our time talking about today. So for CO2 storage, there are a number of different, we call them trapping mechanisms. So once we inject the CO2, these trapping mechanisms are what keep the CO2 in place, right? And so I'm showing a few images here, and then I'll talk about this plot. The first image that you see top left is what happens, it's this cartoon of when you inject CO2 into one of these reservoirs, these porous reservoirs, it's actually less dense than the native brine. So we're typically injecting these into very salty formation fluids. So the CO2 is buoyant and it floats to the top. So we really rely on this overlying cap rock to stop the upward migration of the CO2. So this here is our primary acting and most important trapping mechanism. The next thing that will happen, or one of the things that can happen, is that the CO2, if we're looking at a pore scale image here, I don't know if you can see my mouse, but what happens is that the brine is the wetting fluid and the supercritical CO2 is the non-wetting fluid. And so it ends up getting trapped in these little bubbles in particular areas of the pore space. And actually a good portion of the CO2 gets trapped in these bubbles in the pore space. And so the goal is to immobilize the CO2. And so this is one of those mechanisms that does immobilize the CO2. This is called residual CO2 trapping. This is what my entire dissertation was about, was, how does this happen? How can we enhance it, etc. Another key mechanism is dissolution or solubility trapping. So CO2 over time, the supercritical CO2, it's injected as sort of like a gas phase. It dissolves into the brine. And so the CO2 that is trapped in these porous spaces ultimately will dissolve in the water around it. And then it becomes much denser than the in situ fluid. And what you see here, you see sort of these fingers. These are flowing downwards. And so once the CO2 is dissolved, it actually sinks to the bottom of the formation, which is great because that keeps it from traveling upward. So this is called solubility trapping. Fun fact about this solubility trapping, just to put this in perspective, we're injecting the CO2 when it's in a supercritical phase. It's about, I don't know, a mile underground roughly. And under those pressures and temperatures, the amount of CO2 that is dissolved in the fluid is about 50 times what you would see in a pop or a beer. So when you crack a beer, imagine 50 times the CO2 exploding out. So I don't know, I always like imagining that. And then the last and most long-term mechanism of trapping CO2 is in the mineral phase. And so what you're seeing here is a core. In that commercial, they talked a little bit about the Wallula project. So this is a core of basalt. You see these nice vesicular pore spaces. So when they injected CO2 into this basalt, it reacted, and this white area that you see here, this is mineralized CO2, this carbonate minerals. And so this solid form is, of course, the most secure way of immobilizing CO2 in the subsurface. So these are our 4 mechanisms of trapping. When you look at this plot on the left, many of you may have seen this, it's often shown. The y-axis is showing the trapping mechanism contribution. So if you think about, the total amount of CO2 that got injected, what immediately, so the x-axis is a time scale. And so for sandstone, for instance, 1 year post-injection, the majority, so maybe 80% of the CO2 is being trapped by that structural trap, by the cap rock. A smaller percent is being trapped in those residual bubbles, and some percentage is immediately dissolved. And then over time, this is a log plot. So once we get into the tens of years, we get this increasing storage security because these other mechanisms start coming into play in larger proportions. So over time, more residual CO2 trapping is occurring. The solubility is more CO2 is being dissolved. And once we get into sort of orders of tens, hundreds, thousands of years, ultimately we're ending in this mineral trapping phase. So that's what this chart is showing you. Now, what you'll notice is that the sandstone rates and the basalt rates are very different. The sandstone rates, it takes a lot longer to immobilize CO2 in sandstone than basalt. Of course, there are some advantages to sandstone in that there's typically more pore space, but I just want to point that out. So let's talk about that storage in basalt a little bit more. I want to highlight this project in Wallula. This was really a big deal. PNNL conducted the first, and at this point still the only, injection of supercritical CO2 into a basalt reservoir in Wallula. So this picture that you see, these are basalt outcroppings. If y'all haven't been to Washington, this was a surprise to me when I moved out here. This is what most of Eastern Washington looks like. So you have this really, sort of striking columnar basalt and this shrub steppe environment. So this is what the area around the Pacific Northwest National Lab actually looks like. So the idea was that they were able to inject supercritical CO2 into these fractures and pore spaces in the basalt underground, and it actually mineralized in 2 years. We were able to see that mineralization occurring in just 2 years, where in those sandstone formations, it takes much, much longer. This is again, I don't think I can overemphasize how big of a deal this is, because it offers accelerated risk reduction for CO2 storage. The other thing is that this opens up areas. Basalts represent the dominant rock type for us here in the Pacific Northwest, also in India and offshore. So, this is addressing, I think Raj may have mentioned this, I can't quite recall, but long-term reliability of storage is one of the largest barriers to that CCS investment. So hopefully this can address that. If you'd like to know more about this project, I do encourage you to take a look at one of our most recent papers. I'll go ahead actually now and throw a link in the chat. This one's from 2020. There are quite a few papers that have come out about this project. This is just the most recent one if you want to learn more about this process. All right, so the next project that I'd like to highlight, this is actually the first project that I had when I started at Pacific Northwest National Lab, and this is CO2 storage by sorption in gas shales. So up until this point, when we started this project, people had been injecting CO2 into shales in order to enhance gas recovery. And there had been a good amount of research done on, okay, well, what's happening between the CO2 and the organic matter? So when you inject CO2 into these gas shales, it preferentially sorbs to the shale, and it ends up knocking off or desorbing methane molecules. And so what happens is this image is showing my model. This is a plan view of horizontal wells. We'll have a production well, like well 1, producing natural gas in the form of methane, and we'll have an injection well, well 2, that's injecting CO2. And in this particular example that we were investigating, we did have enhanced fracture zones. So the idea was that we had a naturally fractured system, that we enhanced the fractures between the wells. So where the gridding is more refined, these are areas of essentially what would be fracked to enhance the production rates. So we got to work with our experimentalists on this one, because what we wanted to know was not just what that relationship was like with the absorption of CO2 on organic matter and desorption of methane off of organic matter, but we also wanted to know what was going on with the clays in the system. So Dustin, in the previous talk, he was exactly right. The composition of the rock or the reservoir that you're injecting into is incredibly important understanding, and really does control the end result of whatever operation it is that you're performing. And so we performed these laboratory experiments with cores we isolated montmorillonite clay, a montmorillonite clay core, and then we were also using some organic matter. We performed some experiments where we were doing basically flow through to try to measure what that competitive sorption looks like. So as you inject the CO2, how much methane can we actually knock out? This plot, the one that looks like Christmas, the green and red plot, is showing our experimental analysis along with some fits to some Langmuir isotherms. So the methane data is shown in green. What we see here is that the sorption of methane to montmorillonite, is sort of behaves in a way that we anticipate. It follows this Langmuir curve. What was cool about this is we found as we inject CO2, these red squares, the x-axis is pressure. So as you're injecting CO2, it's a gas phase, gas phase, gas phase, gas phase. And then right around here, we hit the supercritical phase and we get a bump in sorption to montmorillonite clay. So what we found was that if we can operate with supercritical CO2 and in systems that are deep enough to support supercritical CO2, we can actually have this optimal sorption of CO2, which will then knock off the methane. Now, as you increase the pressure, the CO2 actually starts coming off. This is a really fascinating mechanism that has been observed in some prior studies. So, of course, the Langmuir, the dotted line, really doesn't predict the behavior of this CO2 very well. So that's just sort of an interesting tidbit that I learned from this. Now, this middle plot is showing the CO2 to CH4 sorption ratio. So when you inject the CO2, what it's saying, it's CO2 over CH4. And so these numbers, these plots are showing that the preference of CO2 to be sorbed, right? So these numbers are over 1. So this is showing the preference of CO2 to be sorbed to montmorillonite, this bottom line, as pressures are increasing. And this solid line plot is showing the preference of CO2 to be sorbed to subbituminous coal, which was our organic matter, as pressures increase. So again, we are using this information to then design what these enhanced recovery systems should look like. This last plot is showing us the results of the flow through test. And so what we see here, the dotted line on the bottom, that we're just tracking the water that was coming out of the core. That was maintained pretty constant. And then the next to bottom line here is showing the CO2. And so over time, these are simulation results actually based off of what we saw with the model. Over time, we do see CO2 breakthrough in the production well. And so we can get some sort of sense for, if we inject a certain amount of CO2, how much of it will actually stay in the formation, just as a secondary effect. And of course, my interest is always trying to capture or store the CO2 in the subsurface. So that's this project. If you want to know more about this one, we have a paper out. I'll give you a link in the chat for this one too. So yeah, this one is first author Diana Bacon. She was actually my postdoc mentor. Okay, so now I need you all to do a palate cleanse because this is the next project that I worked on at PNNL. And so in this case, I was studying CO2 storage in hydrates. So we were trying to use hydrate guest molecule exchange. Now, when I came to the lab, I had never heard of hydrates before. Some of you may have heard of them, maybe not. Hydrates are very cool. I encourage you all to Google them after this talk if you haven't heard of them. They're sort of like ice, but they have a different structure. And the idea is actually that you have these cages of water molecules that form around a methane molecule. And so again, it sort of looks like ice. It's formed in cold temperatures and high pressures, and it's this crystalline ice-like structure that is capturing methane. This stuff tends to form. We've got some hydrate formations actually off the coast of the southeast, but then also up in Alaska. It tends to be in unconsolidated sands. And so what happens is the hydrate forms and then it consolidates those sands. So it makes them more structurally sound. That's an important comment that I'll talk about in a moment. So what we were trying to do is, again, I was working with some experimentalists. I was doing the models, they were doing the experiments, and we were trying to understand how we might be able to use CO2 to extract the methane from these hydrates. So prior to this study, or maybe more traditionally, if we can even say that, with methane production from hydrates, what had been happening was companies, oil and gas companies, would inject nitrogen into hydrate formations, and the hydrate structure would collapse and the CH4 or methane would release. And so that's great. They're able to produce a ton of methane. But as I mentioned, these hydrates are formed in unconsolidated sand. And so when you break that hydrate structure, it destabilizes that sand and it can have some, negative impacts, I guess I'll say. And so what we were trying to do was inject a fluid mixture of CO2 and nitrogen. This is because CO2 hydrates actually preferentially form around CO2 over methane. And so what we can do in this process, we still don't exactly know how it works, but sort of the best way I can explain it is that when you inject nitrogen and CO2 together into these methane hydrates, it's almost like the nitrogen weakens the structure of the hydrate enough that it, kind of props the door open. And the methane molecule is released and the CO2 molecule is entrapped. And by doing that, we are able to both store CO2 and preserve that structural integrity of the hydrate formation. So what we did in the lab, we have this depiction here that is clearly not to scale. But the first step, we needed to form hydrate. So we formed a methane hydrate with this flow through. You see, we had gas cylinders of each gas that we needed. That went through chilled tubing to get it to a very cold temperature. And then we had this sort of circulating chiller wrapped around the whole core that was keeping everything cold. This was in a foam cooler, actually, that was packed with ice. So we were trying to keep a really, really cold, pressurized environment. And we just ran methane and water through this system until we had formed hydrate. After we formed hydrate, we then injected CO2 and nitrogen, and we did that for a little while, measuring the composition of gas that came out, and then we actually basically turned off the refrigeration components and allowed the system to heat up so it would dissociate, is what we call it, and we just wanted to observe what that looked like. So what I'm showing here is the process I just described. The upper left plot is showing that it's sort of the hydrate formation or association phase. And so we had probes, let's see, these 1, 2, 3, 4, 5, 6, 7, 8. These are probes that we are taking readings from. And so each probe is showing us the temperature in the core as we were cooling it. And then this top plot on the right is showing the temperature within the core as we were injecting that CO2 and nitrogen. this is a really cool reaction. As hydrates form, it's actually an exothermic reaction. So these bumps that you see are these moments where the sorry, I should say dissociation. So when hydrates dissociate, they let off heat. And so as we're exchanging the methane and the CO2, we're seeing these sort of bumps in temperature that we were trying to control and keep the system cool. We didn't want it to dissociate too much. So these plots on the bottom are showing the gas mole fractions of the effluent. What this one is showing, the one on the bottom left, is showing the gas composition during the flow through stage. So you can see the nitrogen being produced, the CO2 being produced, and the methane being produced over time. So of course, in the first 10 hours of this, we were pushing out a lot more methane. And so we did this until we got to what we consider to be a relatively steady state. And then we evacuated all of the gas, and that's what this plot is showing. And this was sort of in an effort to measure what was remaining and try to, double check what we thought had been captured. So what we ended up observing, that's our paper. What we observed was that there was this preferential exchange between CO2 and CH4, and we were able to glean some information about the kinetics of this type of reaction. And so then we built these kinetics into our numerical simulator, STOMP, so that we could model these kinds of systems, on a field scale and design experiments for some of our partners up in Alaska. So I know I'm power talking, y'all. So if you want to read more about this or hydrates, we've got a paper out on this in the Journal of Natural Gas Science and Engineering. I don't expect you to, I don't expect you to memorize or understand everything. I'm hoping that what will come out of this talk is a peak in your interest. Okay, so I'm going to need you to do another mind wipe. Now let's talk about some other work that I've done at PNNL. One of my actual professional passions, as lame as it sounds, is building software tools. So, it's really, really cool to understand how these mechanisms work, how the science works, and to perform the kind of experiments and field studies that I was just talking about. But where I really find meaning is in being able to enable stakeholders or, these actual oil and gas companies, operators, to take advantage of the research that we're learning. And so part of what we're doing in the SMART initiative, Raj mentioned the SMART initiative, part of what we're doing is building tools for people to be able to use. So we are trying to embed this really, cutting edge science in tools that people may be able to use for decision support and risk reduction for CO2 storage. So the overall SMART initiative, again, it's funded by the Department of Energy, Fossil Energy, and it aims to leverage recent advances in science-based machine learning, I'll talk about what that means, to significantly improve the efficiency and effectiveness of commercial scale geologic carbon storage. There are, I believe, 7 tasks at this point. So I believe the initiative is made up of 7 tasks. And I am a co-lead of task 4, which is called real-time forecasting and history matching. So you see here, we've got a number of other national labs and universities working with us. That's actually one of the coolest things working for a national lab, are the amount of other organizations that we get to collaborate with. So this is ongoing research. What I'm showing here is this software platform. I was trying to make an engaging figure. The idea with our software platform is that we're trying to modernize CO2 storage forecasting and history matching with machine learning for real-time applications. What I'm showing in this box is what we did. We sort of conceptually drew out, okay, well, what do we do when we are performing a history match for CO2 storage. And the first step, again, hopefully you can see my mouse, is that we run simulations. And these simulations, we're looking at a plan view here. We run a bunch of different simulations to try to understand, what is the CO2 plume going to look like? How far will it expand from the injection well? What will the pressure perturbations look like? We call it a pressure plume. And so we run, we generate what we call an ensemble, which is basically a group of models with different, porosities, permeabilities, and things defined so that we can try to get a feeling for what the potential outcomes could be. So we run these models, we come up with some sort of initial forecast. So maybe the plume metric in my case is, the area, the footprint area of the CO2. And so over time, we are predicting how large is that footprint going to grow. Each one of these simulations is going to produce a slightly different prediction. And if we are to use different tools, so let's say we use a Tough2 simulator or a STOMP simulator, those will be slightly different forecasts. What we're doing in SMART, and this is actually Raj's task, not mine, they are designing machine learning methods that can learn about these forecasts and try to be able to predict them using machine learning methods. The machine learning methods are learning from these ensembles, and then they are able to rapidly predict, what that CO2 might look like for a scenario. So basically, we learn from simulations, and then the hope is that you could then go and apply it to a site of interest. So depending on the machine learning method, just like with the numerical methods, there is some uncertainty depending on the kind of forecast. So this is our first step, right? Our first forecast. Once we actually start injecting, we start taking, observations. So we start deploying monitoring instrumentation, right? And so this is, true of any subsurface operation. At this point, we start collecting monitoring data. We start collecting data from the wells. We start collecting data, using geophysical methods. And we take this data, we assimilate it, and we update our models, right? We're going to try to constrain our models to reduce the uncertainty. That's what this pink highlight is showing. And so we do this over time, over and over again. We just keep updating our models and updating our forecasts so we can constrain this uncertainty and have a better and better prediction of, in this example, what the area of that plume may be. So this is a typical history matching procedure. What we're doing on SMART, and this is really what we're doing on my task, is we are infusing all of these different steps of history matching with machine learning. So instead of just, collecting data and processing it the traditional ways, we are trying to learn from machine learning so that we can process that data faster. And in some cases, we can even process that data on site in real time. This is particularly, I guess, transformative in the geophysical space and the work that they're doing in geophysics on SMART, because sometimes with these seismic surveys, it can take months to interpret the results of those surveys. So there could be like a 6-month turnaround time between the interpretations and the actual forecast updating or prediction updating. So we are trying to come up with methods that can help us autonomously interpret the geophysical products. We're also using machine learning for the actual data assimilation. So we have what we call disparate data streams coming in. We've got data coming in from the wells, that's, point source and maybe continuous. And then we also have these geophysical products that are, spatially continuous, but are temporally chunked, right? So we've got this disparate, is what I mean, different types of data coming in. And we need to figure out how can we integrate or combine this data so that we are really exploiting it to the maximum extent. How can we use this data to inform our models and our predictions to the maximum extent? So we're using machine learning to learn about the relationships between monitoring types. We're using it to actually perform the model updating itself instead of going back and rerunning really computationally intensive numerical models. And we are using machine learning to do, VOI stands for value of information analyses. So we're trying to use machine learning to glean, what is the most fruitful or cost-effective type of monitoring that we can be doing. Monitoring tends to be an expensive process to undertake. So, how can we use monitoring to the most effective end? And what we do, so we take this information, of course, we update our geo models. That's what this is really saying. That's how this is a loop. We take this information, we update our geo models. We may need to rerun some models, and we end up with these improved predictions. So again, you don't need to understand everything there is to know about history matching. What I'm hoping that you take away from this is that what we're looking at on SMART, at least in this task, is modernizing traditional history matching methods by infusing machine learning at different locations. And, oh, I forgot I had this to show you. So this is actually a GIF that my postdoc generated for me. So there's a lot of different figures on this. We won't go into it in depth, but the whole top row is showing you what our sort of initial, this was our truth. We knew what, in this case, we knew what simulation, or what, I'm sorry, geologic properties we were trying to find in the history match. We set a true, right? And so this is showing us the true porosity distribution in plan view, the true permeability distribution in plan view, the true Young's modulus distribution, again in plan view, and the true Poisson ratios. So these were parameters that we were interested in this example. The second row is showing you, it's just a little GIF of the iterative procedure in updating this model. This is actually as quick. It's showing you, the GIF, as much as you see it moving around, this is actually as quickly as it really does work. And then the third row is showing you how the pressure, in this case, this plot is trying to predict pressures at a particular observation well over time. And so the red dots are observations, synthetic observations that we were feeding the model, and the black wiggles are our predictions trying to find it and improve. Of course, it's on a loop, so it's not getting worse, it's getting better. So it's showing us how we may predict pressures, how we may predict saturations. Again, this is at a particular well bore. And this bottom line, we don't really need to go into, but it's showing we use a PCA analysis for that data assimilation. So for those of you that know what PCA analyses are, maybe this is a more relevant plot. The last thing I'll talk about is some of our work on NRAP. So this, again, Raj mentioned the National Risk Assessment Partnership. We are developing all sorts of tools. Those reduced order model tools are a big focus, but there's also this focus on optimization. It's not letting me play it for you, which is unfortunate, but I have a little GIF here that shows you how the DREAM tool works. It stands for Designs for Risk Evaluation and Monitoring. And so this software optimizes monitoring correct configuration to detect leakage in the subsurface. I wish the GIF worked for you, but that's okay because I've got this other image maybe. Let's see. All right. It's taking you right to the paper. Here, let me quickly update this slide for you. Okay, so this slide is showing you, I know it's grainy, but it's showing you the output of the DREAM model. And so what we're doing with this tool is we are reading in those ensembles of simulations that I talked about with the SMART initiative. In this case, these are ensembles of simulations simulating potential leakage. So in this case, it would be if there was a fracture or imperfection in the cap rock above the CO2 formation, and CO2 leaked through that imperfection into an overlying drinking water aquifer. What would happen, basically. And so we are simulating these worst case scenarios so that we are able to avoid them. What this output is showing you, we don't just look at, well, what if the CO2 migrates? We look at the impact of that. And so the CO2 migration can bring with it heavy metals from the formation, the storage formation. It can also dissolve different constituents that are in the overlying aquifer. And so there are definitely geochemical impacts of CO2 leakage. The yellow here is showing you impacts to pH of CO2 leakage. So you can almost see where the CO2 leaked. I'm not even showing you CO2 in this image. I'm just showing you all of the secondary impacts of having CO2 leakage. So you see these changes in pH throughout this overlying aquifer. That's the yellow. The red are changes in total dissolved solids. So as the CO2 is leaking, it's actually bringing brine and other dissolved components up with it, and increasing TDS in particular areas of the drinking water aquifer. The blue is arsenic. It's hard to see the difference between blue and purple, but they're actually together. So blue is arsenic, purple is chromium. There's a lime green in here that's cadmium. We've also got some lead, which is sort of hard to see. But really the takeaway from this is that we are simulating, okay, these worst case scenarios. And then what DREAM does is it simulates placement of monitoring wells, and it will come up with a monitoring design to tell you, what the best monitoring network is. So anyways, this won an R&D 100 award along with the other NRAP tools. The whole tool set was part of a package. And if you want to read more about that, I'll also link you to this paper. I know that I've gone way over time. So I told you this is our favorite thing to do, talk about our own research. So I'll just stop there and I'll ask for questions.
Thank you, Dr. Catherine.
Sorry.
No,
sorry, Kyla.
we're gonna actually, I think, skip questions, and if you have any questions, please feel free to email. We can post the email in the chat. It's right there as well.